Hello. We're going to do integration by parts. We're going to do it in two videos. Hopefully the videos will be fairly short. It's going to feel kind of weird at first, but it's not too bad. So integration by parts is a method of integration for taking care of integrals that are really kind of hard or impossible to do otherwise. Kind of like U substitution. Remember when we were doing integrals and we kind of found some tough integrals and we found a way to do it called U substitution? Integration by parts is similar to that, except it's just a little bit more weird of a formula. So when I normally do this problem, I'll just throw a equation or throw an integral to students like this one. Find the integral of x cosine of x dx. I let students try it for a bit, and pretty much they start finding out that it's really hard to do and they can't do it. U substitution is a great way to try for this, but then they find that it's just not working and they kind of get stuck, which is kind of the point because you can't do this with U substitution. We need something called integration by parts. So that's what we're learning today, integration by parts. We're going to do an example first, and then we're going to explain where the formula comes from. Just because it's a weird looking thing, it's nice to kind of see an example of it first. Then I can explain where the formula comes from. Hopefully that'll make sense to you for why integration by parts works. And then it's just going to be practicing more of it. The second video will have a specific type of integration by parts when you have to do it repeated times or do something called looping. That will show up for the next part. All right, so quick example. Sorry. Here's the formula for integration by parts. It looks weird. It says to find integration by parts due to the integral of u dv equals u times v minus the integral of v du. That looks weird because all of a sudden you've got u's and dv's and they're all over the place. It's kind of weird. We're going to break it apart and it shouldn't be too bad for you. So we're going to do that same example problem that we had trouble with before. I got to move my screen. Hopefully that works just fine for you. Hopefully you can see this. I know sometimes sorry, I'm babbling. I know sometimes I am moving you might not be able to see it. I am moving my video around the screen right now. It's possible that the video seems to be stuck for you guys right up here in the corner. I've seen that happen before with this. If it is stuck up here in the corner, I will just try to make sure I read this part to you. So we're going to be doing the integration by parts formula. It's right here. In this corner, we got to choose a u and a dv that matches this, because the whole point of integration by parts is I'm taking this integral and I'm going to break it down into an easier integral. So this one is x cosine of x dx. I need to have one of these things be a u and the other part be my dv. So over here, for this part, we're going to have u be equal to x. So this becomes that u is x, which means the dv, that's going to be the cosine of x dx. So that's what it says right here, dv equals cosine of x dx. I'm going to move my video. I moved it to the bottom just in case you can't see it. Right up here, it should say dv equals cosine of x dx. All right, the integration by parts formula says if I've got an integral written like that, I can rewrite it like this integral. You notice though that this has more than just a u and a dv. It also has a v and it has a du. So if I've got that u and I've got that dv, I'm going to need a couple more things. This integration by parts formula is going to require a du. So if I've got u, I need to figure out du, which would just be the derivative. So since u is x, du would be the derivative of x, which is just 1 dx, right? Because it really would be du dx, but that dx is moved over here, just kind of like same thing with u substitution when we've done that before. So du is really just equal to 1 dx. This is my dv. If I've got a dv, I'm going to need to figure out what v is. Well, dv would be the derivative of v, so v would be the integral of this. The integral of, or the antiderivative if you prefer. The antiderivative of cosine is sine of x. The dx went away because if you did that little integral symbol, right, integral of cosine of x dx, that's just sine of x. So these are the four things I'm going to be working with. I'm just going to plug them into this formula. So that's the next step. We'll go through it. Instead of integral of u dv, I've got integral of x cosine of x dx, what I was trying to find. Again, that's because u is x, right there. dv is cosine of x dx. So this part changed to that. This integral will be equal to uv minus the integral of v du. So uv would be uv x sine of x, that's where this came from, minus the integral of v du, minus the integral of v is sine of x, there it is, du is just 1 dx, so du is dx. So the beauty of integration by parts is I was able to take this complex integral, which I didn't know how to find, and I could break it down into x sine of x minus that integral. That integral I know, that's easy. The antiderivative of sine, that's negative cosine. So then I can rewrite this as x sine of x minus negative cosine of x, plus c, of course. Since there aren't any numbers here, we have to have that constant of integration. And then you just quick simplification, minusing a negative is like positive. There is my answer. The integral of x cosine of x is x sine of x plus cosine of x, and plus some constant of integration. Let's actually work through why integration by parts works then. Before we do it, we're going to talk about this. So this is the problem we just did. The integral of x cosine of x equals x sine of x plus cosine of x plus c. To see why integration of parts works, what we're going to do is we're actually going to confirm that we found the right answer by taking the derivative of this side, right? Because if the integral of x cosine of x is equal to this stuff, if I do the opposite of integration, if I do the derivative of this should equal x cosine of x if I did it right. So we're going to just double check to make sure we did it right. Derivative, so d dx, derivative of x sine of x plus cosine of x plus c, right here. If I tried that derivative of x sine of x is going to require a specific rule. That's going to require the product rule, right? First times derivative of the second plus second times derivative of the first. So first is x times derivative of sine is cosine plus second is sine of x times the derivative of x is 1, so just sine of x. And then we keep going, plus the derivative of cosine. Well, derivative of cosine is negative sine. That's where this comes from. Plus the derivative of a constant. Well, derivative of a constant is 0. That's where this came from. Do a little quick simplifying. You could see the signs cancel out. And hey, looks like we actually ended up right where we expected to. We must have found the right answer. As you can kind of see, this integration by parts thing, that has to do with derivatives that required a product rule. So some people like to think of integration by parts as the product rule version of integration. If you like thinking of it that way, that sounds great. So where did the integration by parts formula come from? It came from the product rule, which shouldn't be too surprising because we were just talking about how when we took a derivative that required a product rule, integration by parts was a way we could undo that derivative. We could figure it out. So if you take the product rule says if you take the derivative of a product, it's first times derivative of the second, so u times dv dx, plus second times derivative of the first, v times du dx. We can take that equation, since we know it's a true equation, and we can rearrange the terms however we like. And the way we're going to do this one is we're going to take this u dv dx, we're going to get it by itself. That's why it's here by itself. And to get it by itself, you got to subtract that v du dx. So u dv dx is going to be the derivative of u times v minus v times du dx. Since these are a bunch of derivatives, you can take the integrals of everything. That's right, that's one of the things with integrals, how it works. If you take the integral of something that's being added, you can take those integrals separately. So if this equation is true, the same equation is true for all of their integrals. So we integrate everything. And when we do that, integrating u times dv dx with respect to x dx, these dx's cancel out, and I end up with the integral of u dv equals, this is the derivative, this is d dx of u times v times dx, but that's, those dx's are going to cancel out, right? That's the opposite operations, the integral of a derivative. So that ends up just being the u times v. Like that integral kind of takes care of itself. Minus this integral with respect to x, again, the dx's cancel out, I end up with v du. That is the formula for integration by parts. That's why it works. It's straight up from the product rule. All right, once you have this formula down, it's really handy to take care of integrals that we need. You may have noticed you have to pick a u and a dv, right? So whatever integral you're trying to find, you want to write it up so the integral of u dv. So the way we did it before is I told you for this problem, u is going to be x, dv was going to be cosine of x. It is actually important which one you choose for which. To find out why, let's try screwing it up. We'll try it the other way. So here's the same problem before, integral of x cosine of x. This time, let's try having u be cosine of x, this part. And let's have my dv be the rest of it, x dx. So if u is cosine of x, the du would be negative sine of x. Derivative of cosine is negative sine, times dx, of course, right? Antiderivative of dv, so that would be, so antiderivative of x dx would be 1/2 x squared, right? And then we're going to plug it into our integration by parts formula and see how it works. So integral of u dv, well, u is cosine of x, dv is x dx, so that's right, cosine of x, x dx. So integral of u to v equals u times v. U and v are here and here, so 1/2 x squared and a cosine of x, that's where this came from, minus the integral of v du. V is 1/2 dx squared, or 1/2 x squared, right there. Du is negative sine of x dx, right there. And when I look at this, I'd say, well, this integral is equal to that stuff, but that doesn't really help me because this integral is even worse off than I started out with, right? I started off trying to find this thing, which I couldn't do. I rewrote it and I got to this thing, which is even worse. Like, that's just no good. So the question is, what kind of expressions are good choices for u? How did we know that u shouldn't have been cosine of x, that I should have had u to be x? And the trick is looking what it turned into. When I chose u to be cosine of x, this other one just got uglier, right? But when I chose u to be x, the du was just a dx and it made it go away. So integration by parts. The goal is to break an impossible integral to a more manageable one. Big hint here. Choose your u in such a way that du dx becomes simpler and or that the variable disappears altogether. Let's try it. Here's one that requires integration by parts. It's an integral of t times e to the t dt. For this problem, which would be a better choice for your u, the t or the e to the t? I'm going to go over this answer next. If you want to try it on your own, pause the video, give it a try, and then hit play again. All right, if you didn't pause, or if you did pause and you're back, here's how we're going to go. The good choice for your u in this case would be t, which means all the other stuff, e to the t dt, that should be your dv. The reason t is the better choice for u is when I take the derivative of t, the derivative of t is just 1, variable goes away, so the derivative of u, du, would just be dt, right, 1 dt. This is dv, I'm going to need a v, so the antiderivative e to the t dt, well, antiderivative e to the t is still e to the t, so these are the u's and v's and dv's I'm going to use. A lot of people find it really useful to write this integration by parts formula out first. It just helps them keep track of what goes where and make sure they have everything. In this case, we can double check u dv, well, u is t, dv is e to the t dt, that's all that stuff, so that works out. It's going to equal u times v, in this case, t times e to the t, t times e to the t, minus integral of v du, so minus the integral of v, which is e to the t, du. And in this case, du is dt. And I look at that integral and I'm like, oh, that's easy. The integral of e to the t is just e to the t. So we do that. It's going to be this minus e to the t plus, don't forget your constant of integration. There's my answer. That is the antiderivative of t e to the t dt. Or if you prefer, the integral of t e to the t dt. That's all there is to it. That is the end of the first video. You give assignment 7.3.1 a try. There's just 4 problems, 4 integration by parts problems that you should try. Definitely try those 4. I would recommend trying those 4 before going on to the next video. It's going to give you a good, solid understanding of how integration by parts works. Good luck.